All right. Hello, everybody. First of all, I just want to say how awesome it is to see everybody here. I'm under the, I guess, somewhat radical opinion that there has been a lot of prohibitive, divisional, progress in cancer, professionally, politically, and all this stuff. And I think with the fear and the debility that cancer brings, these divisions just need to go away. And I'm really proud of CAGLA as a scientific advisory board member, and I think other organizations coming around to realize, like, hey, we're doing things to help a very scary process. Why not just do it together, like clinicians and industry and research? And so from the bottom of my heart, my wife's heart, who also practices oncology in Baton Rouge, we practice alongside each other. Thank you so much for spending your time here and for what you do. I get to see the ripples of what you all do a little bit more in the patient room, but just know they're there. And I think it's even more, demonstrative that you do what you do and not be able to see the actual outcomes and improvements. And so I'm deeply humbled to be here. So thank you. So with all that said, I'm giddy to announce the keynote speaker today. I'll give you a story. It was one of my first kind of national talks at ACCC a couple of years ago. And I was nervous. I'm giving one of my first ones. And Scott and I were opening up that conference in West Palm Beach as the AI guy of Google. His presentation was literally, I'm not kidding, like 6 dimensions. It's like it was in your eyeballs and in your face and all this stuff. And I had to follow his with my Microsoft-compatible 1992 to 1994 .ppt. And it's amazing he still spoke to me. But, he's a good friend now. He's one of my biggest mentors. We text weekly and now recently business partners. So I'm super humbled to introduce him. So with his more formal introduction, Scott Penberthy, who, by the way, started MIT, which is no small feat, at the age of 16, is the Director of Applied Artificial Intelligence in Google Cloud's Office of the CTO, a team that works with some of Google Cloud's largest customers to solve their most complex business problems and advise Google on emerging trends across industries, geographies, and technology. A self-described student of deep learning, he's working with healthcare providers and as a side project with NASA on how we can better understand both life and the universe. Scott uses AI to discover new cancer drugs, diagnose conditions before they're evident, which you're going to hear about today, and eliminate pajama time for oncologists. I want to say you want us to have pajama time, hopefully. We all deserve to live longer, healthier lives without this scourge of cancer. It's kind of the philosophy on which he operates with. His brother, by the way, is also a very well-known thought leader in radiation oncology, David Penberthy. And Scott himself has a rich background in financial services and enterprise computing. He was recently managing director of the CEO's office of PwC, leading a transformation of PwC's technology from on-premise waterfall computing to public cloud with DevOps. Scott has many raucous stories, from selling public cloud amid the Snowden scandal, coordinating leaders across Europe, Asia, and the Americas, debating regulation bodies and lawyers, aligning vendors, clients, and partners on a common mission, and finally educating boards and accountants on the wonders of public clouds and AI. And if you don't know what that is, maybe if we have time, you can kind of explain a little bit, because I've learned a lot. Before that, Scott played his hand as CTO at several web startups after rising from IBM Research to the IBM Chairman Office in the 1990s. So with no further ado, Scott Penberthy.
So Sanjay, I've got 2.5 hours for this talk, is that correct? Okay, good. So you guys have a good nap for this. This is, bring this up for me? That's not my talk. Okay, there we go. So I'm really excited to be here. This journey for me started when I was a kid and actually wanted to be an astronaut. And I went to MIT and I remember taking a test and I failed because my eyesight was 20/25. And so I walked across campus kind of dejected, and there was a sign for my future. And the sign was sketched with a marker, and it said, "Free beer." And so, being dejected as I was, I followed the sign upstairs. And there's this really old guy when I go upstairs, and his hair's on the side like this. I think he was almost 50 at the time. And I was 16. And that was a guy named Marvin Minsky. And he was sort of the father of a lot of the AI. And Marvin, I remember taking a course at MIT in 1984. I was sitting there on the LIST machine. It's a very early AI machine. And I'm playing with something, writing a homework assignment. And it was neural networks. And Marvin comes by, mentoring, and he goes, "What you doing?" I said, "I'm working on neural networks." He goes, that shit never works. He walks away. And the reason is that he was convinced that this idea of trying to take something from 1946, where what the insight was in 1946, if you look in the neocortex, the folded napkin in our brains, and you see this white stuff, he said what you're doing is the idea was you're actually storing statistical separation. That you're biologically storing, you're seeing these patterns over time and time again that separate and that makes things distinguished. And he thought that was a crazy idea because you could store CAT, C-A-T, in just a couple like of these tubes in a computer. To do CAT in 100 billion neurons, that's intractable. So the community that did AI for a good 30 years, they couldn't get funding at MIT, couldn't get funding at Stanford, couldn't get funding at any Institute of Technology, Oxford, nowhere. They had to go to Canada. It's cold up there. And now Canada is the seat of modern AI as a result. And Jeffrey Hinton and his friends, they spent all the time trying to figure out how do we take the brain and create an artificial neocortex, which seemed like a crazy idea. And that brings us to this talk here. That technology, there's a gentleman named Leroy Hood, who's sort of the founder of the Human Genome Project. He's now 85. He does 200 push-ups every morning, 200 air squats, and walks a 5K before 9 a.m. every day. Big fan of longevity. So he's my mentor. I talk to him every day. And he had this idea. He calls it phenomics. He said, if I could just get, this is Lee, if I could just get the data for 1 million people over 10 years, longitudinally, and store it, I want to get the genome, which that's the static piece, but I also want to get what he calls all the phenotypic information. He calls that a phenome is a snapshot in time, right, of your metabolites and everything else. If I could just get that over 10 years, guaranteed we completely change sick care to health care. Because he says we can detect things with math using what he called hyperscale AI that you can't see in any instrument today. And there are a number of companies, a couple of them out there now with multi-billion-dollar market caps, that to him are like, those are just examples of a couple modalities of phenome and what the power of this is. And so my hope is today, as I walk you through this, is that I'm a student of AI. I had to eat a lot of crow in 2012 because I was taught neural networks don't work. Oh, they do. And you're going to see today the magic behind that, how that works. And I hope that you get an appreciation for what's going on inside the black box and then start to see the potentials for medicine, and you all are creating it. And what I'm working with Sanjay is how do we help educate you so that you can now use this, much like you use a microscope and MRI. You're not high-energy physics people, but you use MRIs all the time, right? Or you're doing RADOC. And that's the idea behind this talk. So we're going to talk about this rise of phenomics and basically how it's helping with diagnosis. You can see examples just out here. Also, drug discovery is very hot, as well as care and the actual administering and talking to patients. And it comes from this simple idea. It's a lot cheaper and less messy to do things in a computer than it is in a lab. And so the idea here is if you look on the left, you have this diagram, and you start at the top, you have biology. So you're seeing something in the lab, and you record the data that you've seen. Like, does this attack the E. coli or not, right? You're trying to figure out, or does this attack the antigen or not? And that gives you data that you put into technology, and then you run some simulations and says, now try this variant of the molecule and try again. So you're going between in silico in the computer and then actually in the lab. And the idea is if you can go back and forth quickly, could you start to use computers to eliminate the search space? Could you start to use computers to have it simulate and say, how about this molecule? And take that molecule and then go test it and say, oh my gosh, that works. This actually attacks the protein. And so that's sort of the dream of this. And then the idea in phenomics is on the thing on the right. Is he said he wants like everything, like a stew, like all the stuff from a human. And you'll notice where we have a lot of thick lines. So the way to read this is it's a circular chart, and you've got measures around the edge, okay? And you draw a line between them, and the thickness is how well they correlate, how well they relate to each other. And you'll see there's a lot of stuff we have in science around clinical labs, proteins, metabolites, and the human genome. Not so much about the microbiome yet. But we're now starting to discover in these relationships, the idea is that these are called phenomic relationships. And can you find these things and say, these relationships, that indicates cancer. These relationships then indicate a precancer. These indicate you're trending towards diabetes before you even can detect it. And so the idea is, how do you make this, drive this into industry? And we call that sort of the sport of phenomics. But then what I like about phenomics is I was a terrible biology student. I actually hated biology. And the reason was when I took it in 7th grade, it was rote memorization. They would tell you, here's the class of organisms, here's what's happened, or here's a chemical reaction. Well, why? That's just the way it is. Well, why? Because we have experimental data that shows that's how it works. Well, how's it working? Shut up, kid. This is just how things work. And so I never really took to it until I found out about next-gen sequencing. Now, nature has its own language. Being a naive programmer and not knowing nearly what you know in this space, I said, well, can't you just program cells then? And it turns out if you go even smaller, this is from a Nobel Prize just last November. It's called quantum dots. A quantum dot is an artificial atom. They're about 2 to 10 nanometers wide. Now, to give you a sense for what a nanometer is, you hear it all the time, but I really appreciate it. If you look at a ruler, you see a millimeter, the tiniest thing on a ruler, divide that by 100,000. That's a nanometer, okay? Now, a single nucleotide, a single letter is 0.6 of those things. Now, this will sort of blow your mind. Take a millimeter and turn it into a sugar cube, a millimeter size. Can you imagine that, millimeter? That holds 10 to the 6 times 10 to the 6 times 10 to the 6 bits of information. That's called an exabit. 8 of those little tiny sugar cubes, more data than all of the internet in 2012. In your coffee. So the idea is, could we now start to use computers to reason at that scale? And we're all carrying on multiple units of data every day in our bodies. Now, we had this problem at Google. We were looking at actually something more basic, which was we had a way to detect cats in YouTube, for example, and it was using AI. And they said, well, could you do this actually to model humans? And they said, well, maybe, but we don't have enough computers to do this. We needed like multiple Googles in 2014 to use AI at the core of search. And so they said, well, let's throw the book out. Throw the whole thing out. I said, what do you mean how? Well, it's fun. Let's take $11,000, some random number. That was the budget for a summer student, by the way. Take $11,000, try to figure this out. And they restarted, and they said, here's the thing on the far left. Let's forget ones and zeros. What that is a hydrogen atom. And if you look at the electron flowing around the hydrogen atom, it's a single one, there's like 4 wobble states that are called quantum stable states. You can store 2 bits of information in a single hydrogen atom. It's quantum states. And it's shades of gray. It's not 1 and 0, it's 0.6 and 0.4. It's 2 sides of a coin. So we said, let's make that our 1 and 0. So when a computer's reason now, it's not going to reason in 1s and 0s, it's going to reason in probabilities. Okay, that's fine. Well, how are you going to put these things together? And the simple Captain Obvious insight was, well, we have 8 billion examples around us. It's you and I. And so if you see here on the bottom, there's some scans where you say things like Bill Clinton, and parts of your head light up. And you say Obama, different parts light up. If you say Trump, your whole brain lights up. But what ends up happening is if you look at this, that's on the bottom. We're finding these things. There's something about spatial representation inside the brain. We don't know how that works. And if you see, and it's also these multiple layers we found. So if you look inside, there's like layers inside the neocortex. So we had all these ideas and said, how do you combine these two was the idea. And what we came up with is a simple idea. Take all the neurons in your brain, just one type of neuron. Let's say there's 100 billion of these. Put them into a spreadsheet. Now take a snapshot in time, one snapshot, and write down a number between 0 and 1 for each neuron. 0 means it's off, and 1 means it's fully on. And so the idea is that you can have a charge, it's normalized. So that gives you a number between 0 and 1 as a fractional number, and that represents one point in time. The whole thing It's called a tensor. It's a tensor. And I wrote this thing talking to someone at NASA, because we said, well, that's pretty cool. If you think of that as a way to represent concepts in your brain, it's a snapshot. They said, well, the T is the tensor on the right. And I drew this in 2019. We said, well, think of it like everything in your life is like a tensor inside your brain. You see a picture of a bunny, that's encoded as different tensors over time. If you know what the martini had last night, that's also a memory, that's in there. Movies, that's tensors moving through time. And essentially, if you look at the 1,000 Brains theory, which you can read a book about this, there's no light inside your brain. It's just chemical activations. So why couldn't you replicate that inside a computer? And we said, well, this would be really cool, a tensor management system. And look at 2019 on this graph on the left. There's like no interest in the investor community. Like tensors, what the hell is that thing? There's no tensor, that's how we represent stuff. Now, it's one of the hottest areas. They're starting to build databases now to store these values and reason with them. And so what we shifted is, just by looking at the brain and everything else, we said, let's start representing concepts as basically these vectors that loosely represent your brain. And so, well, does that work? Well, this is the secret, this is the person behind the curtain of how you actually see things with a computer. On the bottom, you can take an image, like you see an image, and you draw a square with that. And imagine drawing graph paper over the square, and you write a value in each different little piece, say, well, is that on or off for the red, green, or blue? So you can imagine that, right? Now draw a smaller square, and just like you see in the artificial neuron, connect lines from the bottom one to the top one, just like you see in the brain, except it's a little smaller. And what you want to do is, then you keep doing that, and what you want to do on each different line is you do two simple operations. Either boost it a little, it's called a bias, or you attenuate a little, it's called a weight. And you take the value Wx, weight it, and add a little bias, B, just like the brain. And you fill it with white noise, complete noise. It's called Gaussian noise. And now you ask it a question. So at the bottom, it's an image. At the top, it's a line of lights, idiot lights. And one says cat, one says dog. And you take it off the shelf and you go, here's an image. What is it? Cat. No. And so what you do is you say it's a dog. So it then goes through those weights and slowly changes the numbers on those things and guesses again. You hammer it 1,000,000 times, this thing starts to know, oh, it's a dog. That's exactly what that is. And you said, this actually works? Yeah, it works really well. And they said, well, I want a supercomputer to build this. It happened in 2011. And Jeff Dean looks at his budget and goes, well, I have $11,000. They said, no, this is going to work. He said, well, we need to do this fast. And they said, hey, my kid loves his PlayStation. You know that when you're doing the graphics, could we do instead of drawing monsters, could we draw neurons? And over a weekend, they hooked it up, and it worked. That's NVIDIA. And so as they did this, some other enterprise individual less than 2015 and said, I wonder, could I actually dumpster dive in blood? Dumpster dive inside blood and look for the cell-free DNA and say, could I detect something by reading that and use this neural network to say not cat or dog, cancer or not. And so what they do is they figured out, doing a long time figuring out the custom assay to pull out the right cell-free DNA, and by literally stacking it all just like an image, just like I showed you before, they take the image and they run it all the way through the thing and it goes, cancer or not? I don't know, cancer? No, it's not cancer. You do it enough times, it detected cancer. They said, well, that's cool. What else could you do? I said, well, let's take that, put it in the next one and say, how about guessing the organ of origin, just by looking in the blood? That worked. Okay, how about if I give you that and the organ, could you guess the stage? Yeah, precancerous, no problem. So this is now in trial, using the same technique that used to run on a PlayStation in 2012. Running the same code, by the way. The same code that's in a driverless car in your Tesla. So as they're working on this, the scientists go, well, that's pretty neat, but that's only perception. I love when they say that. It's only perception. This was a dream when I was a kid in school. They said most of the brain that separates us from cows, or most people from cows, is that you can actually understand language. And language is a sequence of these things, right? It's longitudinal, it's over time. And if you look at the computing power to say, let's try a computer, like an AI for every word in a sentence, it becomes impossible. So they got together, a bunch of people in 2017, and they did the thing on the left. It's called an attention network. And this idea was, I know what we're going to do. we're going to do the same thing for cat and dog, but we're going to change the weights based on what we're looking at. What do you mean? No, because it's going to change over time. So all the weights in that huge thing, the billions of weights, it's a big dictionary. Given what you're currently looking at, just change the weights. Isn't that expensive? Yeah, but what? Let's just throw computers at it. And so what it does is it takes the context you're looking at. If you do a prompt in ChatGPT, you type it in. It looks at all different words. So the first letter, the last letter all relates to each other. They're all wired together. And the weights itself it learns are based on what you type it. It's called an attention network. And that basically turned out to be really cool for translating language. And now what we're finding out is that it's starting to look like a universal language understanding machine. So what else is a language? Like biology, like quantum, like the universe, like dark matter. It's pretty amazing. Well, that's one community. Now, the physics people at the departments were feeling left out because AI is really cool. And the physics people weren't playing much. And they said, we got this thing for simulated annealing. Well, what's that? They said, well, no, here's what we're going to do. I have a better way to generate ideas. And here's what we're going to do. If you take an image, you see the image on the right, see of like a downtown. If I slowly add a little bit of noise called heat, it's a heat, you're trying to simulate a physics experiment. So you add a little heat in one step at a time. It's called the Gaussian noise, a little white noise, and you do it again and again and again. At some point, it becomes white noise again, right? Well, why can't you do like the Beatles album and play it backwards? And they said, well, that's a cool idea. And so what they did is you can now learn, basically, given an image, what kind of noise do you introduce at each step to then create the right picture? It's called diffusion models. And then the two teams got together and goes, oh, let's just mix this together. Well, why? Because it would be cool. And what they've realized is you take the attention network on the left, and what you can do now is you can take human language, and then as you're taking the noise out, the human language steers what you want to take out or add to the different image. That's how you get beautiful pictures of cats and dogs now. You can do these things backwards. Well, how does this work in medicine? This won the supercomputing prize in November last year. And what it is called GenSLM. And what they do is they said, can we determine, just by looking at the source code to a virus, just look at the source code, is this a variant of interest? Now, a variant of interest, as you know, that's a big deal, because now you're talking about vaccines, spending billions to go try to take this out, right, and update the flu vaccine. So there's like millions of these, but which one's a variant of interest? In other words, it can really have a bad effect on humans, much different, and it's sufficiently changed from previous ones. So what they did is they took all these millions of cases from COVID, and they basically, instead of cat or dog, they said, interesting, not interesting. Pretty neat. That worked really well. They said, well, can you generate what the next one might be? Like, could you predict what the next vaccine should be before we even see it? So, I don't know. So what they did is they now added a diffusion model to say, let's start with pure noise. Take a DNA strand, make it just completely random noise, and change it over 1,000 steps based on what you see in another network. So instead of generating cat or dog, could you generate a variant of interest given what you see? The answer is, they ran this without seeing the Delta variant. It spits out the Delta variant. People are like, no, that's interesting. This is now sort of like wanting this, like won like the Nobel Prize in supercomputers. It's the nerds who try to make the computers as big as they can. And so this is like what that is, and it's a tremendous amount of computing. Well, you don't stop there. The brain is a very complex, rich, and complicated organ. We're still barely understanding it. And I talked to a lot of people, and they said, well, is this AGI? I said, that's not the right question. That's like asking, is the Mars lander a bird? Because you're trying to figure out, like, we know what human intelligence, we've studied that for years, and we're used to being emotive, and we have the reptilian brain, the higher order brain, everything else, and we're so concerned about, is that going to be just like us? But what we're doing is we're discovering something that has a different type of intelligence, that's a tool that's more powerful than us. And they said, well, what else do you need to add? And they said, well, we need to add long-term memory. So see a lot of things you'll see in the press today about the longer and longer context windows. You'll see that from different people. The idea is, can you now add the entire internet as a memory to every AI? And how do you add sort of that as a context? So that's research. Well, how about other modalities? Modality is a fancy word for other types of data. So one of the researchers said, I have an idea. It's Jay, who runs research for Google. He said, I have two teams that are going to compete against each other. Okay, what's the challenge, boss? Take a small sample, 3 seconds of YouTube data. That's 3 seconds uploaded on a given day. That's 270 million videos, by the way. So take 3 seconds, and then just take, a single frame and 3 frames on either side, a very small snippet, 8 frames per second, kind of, like the early motion pictures. Here's what I want you to do, he told the researchers. Take video, like the cat thing you saw before, turn that into a tensor. Okay. Take the audio, same thing, make that a tensor. Take the text, make that a tensor. And now have it play games. If I give you this video, what's the audio? Guess. If I give you this text, what's the picture? Guess. And do it a few trillion times. What do you get? You get the ability to type in text and generate beautiful movies. And if you then not to be outdone, OpenAI says, that trick from the Gen SLM I talked about where you take the two things and you mix them? They now mix the transformer back into this, and now they're doing a minute-long videos. The reason that's interesting because that's a little bit longer than Sanjay's videos for TikTok. So I'm trying to build an artificial Sanjay because he films it all himself. I just want to type it in and go, Scott, you're so good at this. So the idea is we're now adding multiple modalities, and what's interesting to me about that is a video is like a small snippet of phenomics. Instead of text, metabolites. Instead of images, how about an MRI scan? Instead of text, how about the DNA sequence, RNA sequence? And if you stitch it together, can you start to now synthesize it? So the trick is, if I pull it together, instead of generating a video, no, that's a drug. That's cool. Instead of describing the video, no, that's called diagnosis. You see how that works? So the same technique, you have N different modalities. If you take the N and you're predicting the outcome, that's called diagnosis or treatment recommendation. If you pull out one of the N's and say, guess what's missing, that's called drug discovery. So an enterprising PhD student said, there's a real problem with MRSA drugs. I mean, MRSA in basically these bacteria in hospitals, right? And he did a thesis, and he said, I wonder if I could have an AI figure out what existing drug could I use and repurpose it. So his idea was, it's simple. Just take 6,000 drugs and go test them all. Okay, what's your budget? I don't know, $40,000. So they can't do that. He said, so I'm going to write a computer program to do that instead. So what he did is he took a modality on the left, the molecule itself, and he encodes it into the neural network. So the different weights in the connect, it's called a message passing neural network. So he basically takes it, so you basically have a carbon atom connected to a hydrogen atom and so forth, encodes it to a neural network, and he trains that network to guess, will you attack E. coli or not? So it had 7,000 different molecules that attack E. coli and some that don't. And then it was able to take a molecule and guess, does it attack it or not? That's called pre-training. He then took that and took the MRSA and had a few samples of this and said, here's a new thing we want to attack. Here's 7,000 molecules. Design me a drug. How long do you think that took? So usually, this is like, think of going through 6,000 drugs, combinations of drugs, all different molecules, run in a lab. 48 minutes on his laptop. So that's what I call drug discovery. And so he's doing it 48 minutes. And now we're finding these things, the new things that unfold like 12 minutes. And what's interesting about this is that he said, when it first spit out 240 different molecules. And he treats it like my friends at NASA do. AI is an idiot savant. Which means, that's a nice idea, pal. Let me go test it. So you take the 240 molecules, they test it in the lab, they spit out 9 that might work. Now doctors looked at this, and as experts like you, and said, no, these first 7, they're not going to last in the human body. These 2 are interesting. They're now in drug trial, less than a year after his PhD thesis, right, with very little funding. So imagine what that does to like the pharma companies, right? They're now thinking about this. And they said, well, Scott, the testing doesn't work. Like, talking to Lee Hood, he said, we're trying to get the cost down. And the biggest cost right now for testing is mass spec, because mass spec is still a very expensive thing. NGS, next generation sequencing, that's $100 in the lab. I have a friend at Stanford, and they said, oh, you got to meet her. She's amazing. And she says, who's it? Jennifer. And met for Jennifer, and I go see this Jennifer. And she shows, that's her hand holding this thing up. And she goes, I said, what's that chip? She goes, this is nanophotonics. Does anybody know what nanophotonics is? I didn't either. So nanophotonics is the study of light at nanoscale. And it turns out it's also electromagnetic waves. And what she can do is she basically has these very tiny things that she puts onto the chip that are like sunglasses. And she paints sunglasses on them that 1 molecule thick. And what that does is when you now push blood over this in a serum, blood over this in a reagent, what ends up happening is you shine light through it. Because it's so small, it resonates like Foster's glasses. You know, when the sun, you're trying to block it out, it can know if it's a certain wavelength. So then it spikes. What that means is she can now, she says it's $1. The chip is like free, like a penny. The reagents are all the cost. In 5 minutes, she can detect if you have a particular DNA in the blood. I said, well, how many can do this? Like 1 chip per thing you're looking for. She goes, well, not really. I said, well, what is it then? She goes, how about 100,000? So if you think of like if you use an Illumina sequencer or things like that, you get out a bunch of different arrays and it uses oligos and everything else. This is done in the lab on a box about the size of a shoebox today in the lab. And the box itself costs about $10,000. That's now being developed about 5 miles from my house. And this is, to me, a lot of you probably aren't involved with this. What I'm really excited about is because of COVID and because we're starting to see the mRNA starts to work, this is drugs as code. And I hope I don't botch this for those who are experts in this, but if you look at on the left, this is a pictorial depiction of the drugs for COVID-19. What you have is the green area is sort of like the payload. That's literally code that goes into your cell. When it goes into your cell, you produce that antigen on your actual human cell. And then you have these untranslated regions either side that allow it to sneak into the cell and actually insert into the process of manufacturing the next cell. And that's wrapped into a little tiny particle. It's about 10 nanometers wide, a very small ball, and it acts like a salt. And the way this thing works, it's just fascinating, is when I was talking to the creators of this, they said, no, we turn your armpit into a bioreactor. What? Oh, no, what happens is that is part of these drugs. It's an mRNA-based drug. The code is the code for the spike protein on COVID-19. So when it goes in your arm, it goes in between your muscles, and then it gets picked up and ends up in your lymph node. And then that squirrels into the cells in your she's nodding. It squirrels into the cells in your lymph node, and your lymph nodes produce the antigen on the surface. And if you have a healthy immune system, your body's like, what is that? It creates a T cell, and now you're somewhat immune. Isn't that amazing? It's programming. And they tell me one of the companies, I won't mention who it is, was about to put out a new drug. They said, we just found a new variant. Can you do this one? They're like, we just went through all your approvals for everything else. He said, well, we're working on platform approvals. What does that mean? If you do the same process, everything else, and you just swap out the code, we'll let that go through as a personal vaccine. Cool idea. Well, can you help us? He said, well, I don't know. He goes, create it. How long did it take you? I don't know, 24 hours? They created the vaccine over the weekend, and they said, well, let's put it in a rat first and make sure that that's a normal process to make sure that it doesn't, and the mouse doesn't die. And once they did, that became the vaccine, 30 days. So we can now do personal vaccines, and this is now being used to attack HER2-positive cancer. So instead of 1,273 nucleotides, it's 1,254. And you can literally sample the patient, read what her cell has, put this into a nanolipid particle, inject it into the patient. They produce this in her armpit. Immune system then attacks and removes that particular variant of the cancer. Amazing. On the lower right, mononuclear antibodies. What these are sort of a particular shape, and it has this shape called heavy chain, light chain. It's like this big, heavy thing on the bottom, two little light, looks like a Y, right? But what's interesting is the very tip of these things is like a tool tip. It's like a DeWalt screwdriver. You get it has different tool tips, and those are the things that actually attack the different cells. That's also code. So you can actually program the code in this, and using a different fermentation technique, you can actually produce this. And they're now looking at, okay, I'll approve the DeWalt screwdriver, and then as long as you test the tooltip, go ahead. And those tooltips are personal vaccines for cancer. Amazing. This is now in trials 2 years ago, so we'll see it progresses. It's not yet FDA approved, but this is where it's headed, where the idea is we can start to have personal cancer vaccines and eradicate it forever. I'm a member of this thing called ClinPGX. PGX stands for pharmacogenomics. That's a technique where, a little controversial, can you look at correlations between what's in the gene? As you know, genes are like a recipe book. The restaurant is our body, so we don't necessarily express everything in the restaurant, but we choose what we want. So What this is fascinating. If you look at some of the top drugs, best science in the world, we take them because these are really like heartburn. It's terrible if you live with heartburn. But it turns out, for Nexium, for example, the black is the only one that's actually effective. All the rest may have side effects. It's ineffective. But that's because given the granularity of our science, this is as far as we can go. With phenomics, we can get this down to the individual. As Lee talks about, well, you take Advil? Yeah. Which one? Advil Green. I take Advil Blue. And the idea is, can you start to look at molecules that are designed for that and start to stratify these? But before you even get to there, we're looking at things now. If you can do a phenomic test, could you then go in and go, no, don't take Nexium? But my boss, it's like, I got the worst heartburn. I know you do. It's not going to work. Right? Well, why can't, just let me try. Well, if you take the medicine, there's so many side effects. Typically take another thing for antidiarrheal, and it starts piling on. So the idea is, can we start to introduce this with pharmacogenomics using this to basically reduce interactions, reduce costs, reduce patient complications? So I'm a member of the team now trying to make this a standard called ClinPGX for the world, and we're looking at things in PubMed and publishing this out. So it end up basically, when you're doing your charting, it shows up and says, maybe you think about something else besides that particular drug, and here's the research why. The next thing we're finding is, well, where else can you use this? There's something called LCA blindness. And LCA blindness is a genetic defect in that correlates with one particular letter, one letter in the DNA of the retina of your eyeball. And if you've had eyesight for a few years, you typically lose eyesight about age 3 to 5, and it's a terrible condition. What they're able to do now with CRISPR combined with code is they actually inject into the eye. My uncle had this. They inject into the eye, it goes to the back of the eye, and affects the germline, affects the actual manufacture in the retina. And sight, for those that had sight before, is restored. Now, restored means they can see shadows of light back and forth. If you never saw light, your brain doesn't have the ability to process it. So you have to have had something before. But this is kind of very early, and this is just changing one letter. One letter. I think I'm very proud of David Sinclair. He's been at this for, just like the neural network people at MIT who are told, that's never going to work, right? Same thing for this gentleman is at Harvard. I like to call him the Tom Cruise of medicine. He looks amazing. He's in his 50s, And so he has this theory, and he practices on himself and his family. It's a great book if you read it. And his theory goes like this. You're born in the upper left, and then over time you have DNA damage. And eventually that leads to some genome instability. And then what happens is these cells start to forget who they are, and then the cell still replicates, but as a result, it doesn't really know what to do. It's called cellular senescence. He said, if you talk to David, he'll say that's what gives you the creaks as you get older. You don't feel so great. Why does my arm hurt? Your neck pain, that kind of stuff. He said a lot of it is cellular senescence. So he says, I bet I can. That's just information loss, is his idea. So if I can restore information, I can now be able to basically repair the code and reverse it by basically scrubbing the information and cleaning the disks, so now you have the right information being processed in your DNA. That was finally published and accepted in Cell magazine. I think it tried like 10 years to get it in. But now the community is starting to embrace this because of what we've seen before with the companies and the correlations. We might be able to aging actually might be a disease. And we think the natural aging range for humans is not 80, but much more like 120. People are like, I don't live to 120. He said, no, would you live to 120 if you feel like you're 30? That's interesting. Well, Chris Mason was working with NASA, and I met him through the twin astronaut study. And he goes, well, why should we just stop at our DNA? I said, what? He said, no, we have things, for example, we have eyeglasses, we have artificial hearts, we've got pacemakers. Why can't, and we have, things, if you lose a limb, why not using the DNA of other things around us to augment who we are? And I'm like, well, where would you start with this? And he said, well, let's look at this thing. This is called a little water bug, a tardigrade. And what's fascinating about the tardigrade, it looks like a grain of sand. If you see moss out your backyard, you can actually see these in the moss. You need a magnifier to see these things. What's amazing is you can desiccate them, take all the water out. These are actually on the moon right now, by the way. And you can take them out, and then you add water 6 months later. It's like the chia pet. You add 6 months later, you add water, they start crawling around. Like, how does this thing survive? And so this Japanese, they're all researchers studying this thing, and they look at the DNA, and they published first, and they had a very sophisticated name for it. They found a DNA that causes this. They call it the damage suppressor gene, DSUP, DSUP. And they did an experiment, and the way it looks at it here is like how many of these cells are dying, which is the y-axis, and then over time. And they basically took human liver cells, which you can order like Amazon. That's amazing to me. I'll have a few liver cells. No problem, boss. I'll send them to you right away. So you can order this online if you're a researcher, and you get human liver cells. You then combine that with the DNA here, irradiated it, and sure enough, over time, this actually protected the cells. So he's talking about if you're going to Mars, you have all this radiation, could they actually take a pill and basically have a suntan lotion throughout their body? That's better than any suntan lotion you can buy. And the idea is instead of having to buy a suntan lotion, just take a pill for the month, you're good. Amazing idea. Now, if you think of all this work, we talk about personal vaccines, the problem is, well, how do you get it out there? Like, how do you manufacture this at scale of like the humans? You know, personal drugs, it's a whole different industry for pharma. And they said, well, you just put it in a truck. What do you mean put it in a truck? Well, if you look at how these things are manufactured, there's actually a robot now sitting in front of a bench instead of a bench scientist. And the robot is actually mixing and heating and doing the work of a bench scientist because it's a protocol. And they take the protocol, and now they're shrinking those cells at companies like Ginkgo and others, where now it'll fit in a Sprinter van. And the idea is, could I actually have a clean room that's in a Sprinter van in that environment so that as it's distributed throughout the United States and other countries, the idea is you get a personal cancer vaccine, it's brewed in this thing, available, you get tested Friday, your fresh brew is ready on Monday. And if it's a platform drug, could you actually ensure the safety of it? Now, right now, the brew itself is like coffee. It's like doesn't cost much to actually make it. It's probably a few bucks for actually the canister. It's about $5,000 to purify it because you put it through a special kind of sand that has these oligos on it, and that's kind of expensive. But that's where we're at. Raw costs about $5,000. Today's about $150,000 for this. But that's where it's headed. Now, how do you create these things? It's just code. It's just code. So what they're doing now is they're coding in a browser, amongst each other, and when they're coding, the robots then take the answer and then go test it in the lab, give you data that goes back into your code. So in the old days, when I grew up, you'd take your computer code, hand it to somebody, you wait an hour, and you get a printout back. Now, you code, you wait, robots run the test for you, it shows back up the next day in your browser. So now, imagine how fast you can iterate, and you have thousands of people doing this as drug discovery. So now we're able to actually do fermentation actually in the browser. And then what you can do is go from the sample and basically do all this hyperscale stuff in a simple language called Python. And we're also seeing is now they're building chips. Now we've figured out AI to some extent, and we also look at the sequencing. They're now redesigning computers so they focus on basically this new style technique, and we're looking for a 10 to the 5th, 10 to the 7th improvement. Because right now, to actually do an AI, it takes about 700 watts, which is like a vacuum cleaner. And if you think really hard as a human, that's about 15 watts. And so we're trying to figure out how to reduce that using custom chips. And then what we're also doing is because the data is so heavy, because there's so much data in a human or in an animal, you've got to move these things across the world. So Google actually has its own Navy, and we have our own connectors across the globe, and we essentially then are dragging fiber across this to essentially basically move data around the world as the fastest way possible. And I said, well, how are you going to interact with this? And this is a prototype running on my laptop that I have in the CT office. And the idea is that, well, if you assume AI will be as strong as us in communication, well, how do you interact with it? Well, how do you interact with a human? So what does that mean? Well, you want to talk to it, just fire up chat. You have a question? Call it. You want to talk to it? Zoom it. And so now we're seeing, as you're now starting to see these AIs, where as it evolves, the way to work with these and interact with them is more about security and proving who it is, and basically activating that email, and now you've got something you can communicate with. And as you use this throughout time, it starts to learn and be your companion. And so now, over time, you will have basically AIs as part of your practice and everything else who knows you and all your patients in a private, secure area that's all yours, and you control it, but you interact with it just like you do anybody else in your staff that doesn't have to actually be there. So we wrote a couple of years ago with Lee, we had a special issue of Scientific American where we wanted to talk about this technique called, and we were saying the phenomics revolution, it's coming. I was just at a recent conference on precision medicine, and Lee comes out with this huge smile. He goes, everybody's doing phonomics now. It's awesome. Because what he's talking about is, can you start to take these different modalities, just 2 or 3, and you have a couple examples right out here. Can you look at these modalities, move that into that tensor space, find the patterns, find the cat or dog, and say cancer or not, sick or not, and then move it back into the domain and show where it is on the image. That's the trick, right? Extremely effective. So hopefully today you got a sense of where it came from. I really enjoyed sharing this with you. And if you have any questions, I think we've got, gosh, at least a few minutes for questions. Sanjay? So thank you for your time.
Does anyone have any questions? Hello? Oh. Anyone have questions? You mind coming up, Dr. Boudreau?
That was fascinating and terrifying at the same time.
So what? Oh, yeah.
And I guess my question, which maybe a lot of us have and aren't willing to voice, so at some point in time, I'm assuming this computer is going to figure out that it's smarter than us.
Okay.
Possible or not possible?
Yeah, so define smart, right?
And so at some point, suppose it decides we're sort of superfluous and are kind of a pestilence on the planet and are ruining it. You follow my...
Oh, that's a
reasoning?
real fun debate over...
I know, you could have a few cocktails over that one, but I'm just curious to know your thoughts in that arena.
Yeah, so I think that's a really interesting and powerful debate. It's all happening in a lot of smoke-filled rooms and over scotch and whatnot. And I may have been partaken in a few of those myself. But what we're finding, though, is if you look, you got to think about this. We have superhuman thumbs we use every day. It's called a hammer. We have superhuman wrists. It's called a drill. Right? And so this is one of the first tools that we as a human race, we've created a superhuman tool of reasoning and language. And what I brought up earlier is we talk about, well, is that a human? Is it conscious? Does it feel? Is it aware? Is it going to attack us? Think of it like a rocket. It's nowhere near a bird. Nowhere near as elegant. Nowhere, it can't reproduce itself. It doesn't fly. It's not beautiful. It's this big, honking, ugly thing, but it can get us to Mars. And we're trying to make it more efficient. So that you can think of these techniques we're talking about today. It is a superhuman reasoner, much like a superhuman thumb, superhuman wrist we've seen before, but it's now a tool of thought. And they say, well, how in the world are you going to control this? Like, it's smarter than we are, like a lot smarter. Yeah, it has elephant memory. It won't forget anything either. So, and picture-perfect memory. How do you manage something like that? That's easy. Talk to anyone who manages a research community. Right? Think of like a people who are managing researchers. How do you manage something that's smarter than you? And so you start to think about, this is now a tool you can now use. And what's interesting is this tool will soon be available to everybody. And so imagine a tool that's at your disposal that not only has the reasoning power of asking questions, now your question is, instead of having to write the document, you edit the document. Instead of having to capture an image, you imagine the image, it creates it. So now imagine how fast you can take things out of your mind and make them reality and have a co-pilot that you sit there and iterate with. And that's really where it's headed. And I think that's, in that sense, like the drill doesn't take me over, right? Neither does the hammer, but it's a very powerful tool of us. But because this is a notion of intelligence, what we're seeing, and NeauxCancer says at MIT, he said, these are not tools, Scott. I said, what? It's not a tool? He goes, no, it's a partner. It's a collaborator. And so you think about this is that now, we think it's a foreign concept, but so was a supercomputer in your pocket in 1997. Now we have that. Our kids are going to grow up with, well, of course, Mom, you've got multiple AIs. I use them in first grade. What? Yeah, first grade. Well, what did you do? Like, what was your homework today? It wasn't too much, Mom. What was it? I had a 20-page paper. I had to do a couple pieces of art. And then I had a short movie I had to produce. How long did it take? I don't know, 6 minutes. Can I go play now? Right? So that's kind of where we're headed.
Yeah, I think similar to that note, Scott, I was wondering if you could talk about kind of the concept when you were talking about longitudinal evaluation. some of the examples for a clinician or someone in oncology would be we were using EGF inhibitors in lung cancer if it was appropriate, and we know what escape mechanisms. We learned retrospectively. Oh, this escape mechanism happens, so upgrade with this one that works for that mutation. Or for, CML, like the first generation. We have observed that these escape mutations, have an X amount of probability over X amount of time. So could you go more into that longitudinal concept of, obviously, if you have the data of everything and we're able to get those the million examples of the cat and dog, and you have a very now precise example or timeline of what those escape mechanisms are going to be, rather than the traditional way on where we're, treating it now. It's like, we know there's billions of cells, we're going to get a biopsy, do one regimen with one or two drugs, we know the tumor's evolving, we know it's heterogeneous, and it's just a matter of the progression, when really those things just grew on the one therapy we had at a one moment snapshot in time.
Right.
And I think y'all are talking about those devices where now if you have this dynamic evaluation, like some people don't even redo molecular testing on a progression to stage 4,
Right.
they still go to that biopsy 2 years ago, which is insane. And so, that y'all are working on those things to be able to kind of reanalyze and then also predict forward based on those variations and to the degree which they occur.
Yeah, I think we talked about this earlier, even this morning. And this is how fast this field's changing. I mean, I'm only a student of this. There's like 200 papers a day. It's like impossible to keep up. So it's about your network. But I think what we're talking about here, Sanjay, is that if you look at the latest, OpenAI has Sora, we have something called Lumiere. They're now getting to generating video. A video is a longitudinal sample of multiple modes of information, all synced together, right, by frame. Pretty interesting. Now take that into medicine across hundreds of millions of people recorded in the next decade or so. The machine will have seen and will have the ability to perceive what are different progressions of cancer for these different patients and what were the different phenotypical outcomes for these patients. So now you give it a couple points in time, it can then start to give you and generate, this is the most probabilistic outcome, given what I've seen across the world of how the cancer may progress. Do you want to play it forward and backward in time? We'd like to see how the tumor evolves or not, and here's different outcomes. And that's kind of where we're headed, so that you're starting to figure this out. And what it's reasoning about, Sanjay, which is so interesting, is the fundamental concept is a healthy life is just a shape in tensor space. It's a convex hull. It's just a big shape. That's a healthy life. Our journey through that is just a path through that journey. That's how this thing works. And what's able to detect is if you start to veer off the path, what Lee calls actionable possibilities are the things you can do to steer back before the cancer actually happens, right? And so, what we're doing, what you're talking about here is, once I see enough paths for a few, like 100 million people over 10 years, let's say by 2040, by you have that time, you'll be able to say, oh, this is a typical pathway, and the doctors, your grandkid doctors, will be able to play it back and forth and look at these things, and assume that's no big deal. Of course you can do this. Isn't that amazing?
Any other questions? Oh,
On the left, I
Michael?
think.
Oh, excuse me.
Is that what you're looking for? Good.
Michael Mauney, former linebacker for the New Orleans Saints.
What's going on? That was fascinating. Thank you.
Thank you.
I got a question on more in relation to the compute power and like, is that much of a limiting factor just as you scale this thing with the amount of data that you're putting in these models? And if so, like, where does that intersect with the quantum computing?
Yeah, I
as
think
we
what
move
you're
forward?
seeing now in the chip industry is much like bandwidth was 25 years ago. Bandwidth is like how your connection to the internet. Back then, you used to dial up. It's really slow. It would take like 5 minutes to download a picture. Now we have broadband, so that's pervasive. I think you see now the industry talking about how do we then completely revamp the chip industry, because if you actually truly can get at a superhuman reasoning agent that you can use in your daily work, everyone's going to want one, right? Because it allows us to be so much more productive, and we think at a higher level now. Instead of having to write the paper, we edit the paper, right? Like I wrote a whole page, a whole section of a technical book in about 5 hours, 28 pages, including references to everything else. It was in my head, 10 pages of prompts. They use it as a reference for the book. I was almost embarrassed because it usually takes me 200 hours. This is 5 hours. So back to your question about power, I think we're at an inflection point, much like bandwidth was. The demand's there, and you're going to see a spike, but it may settle back down. But what's also happening is it's a renaissance in chip design. You'll see companies come out. So if you look at a lot of the current chips, we explored lots of different techniques for AI in the last 20 years. This one works. And so what you're going to start to see is you'll see design by committee and design by, I know what works. And so you're going to see us transition to much cleaner designs. And what's nice about that is that there's one that just came out recently where they're now able to go about 100 times faster than the top models just because they focus on what you need. And it's a lot less energy. And we're also looking at is how do you get the energy down by a factor of 10 to the 5th to 10 to the 7th. And the reason is if you think really, really hard and you're studying for, let's say, the boards, your head just hurts, you feel full. That's 15 watts. 15 watts. It takes 6,000 machines running at 700 watts each, 6 weeks to train an AI model. We do it in 15 watts. So that's the gap we're trying to close. And I think you'll see this movement called EAC that you might see online. The notion is we now need to move to physics-based AI. Physics-based AI, instead of actually doing the math, you encode the math in a quantum state or a thermodynamic state, and in one clock cycle, you get the answer back. That's cool, right? And when you do that, this is what they talk about. We want it like ChatGPT and Gemini in a toaster. Except it'll last for a couple of weeks, then you got to throw it out because it expires, because it's a combination of biology and compute. Isn't that neat?
I have a quick one.
Yeah.
There's certain companies that are out there that are experimenting with surgical implants of AI chips into the human brain. One of them, most recently, has gotten a lot of attention from that.
Yeah.
Do you have any big picture thoughts on that, whether or not it could likely work, or what are your thoughts? More dilemma aside.
I'll tell you just a couple of thoughts. One is I'm so glad in the industry there's only one adapter I've ever needed for my laptop, for power. It hasn't changed at all in the 20 years. I think the point is that what I mean by that is that having a general purpose one that we all use, I don't necessarily see that, but I do see things where if we can actually, and there's research now showing that AI can detect things that are happening in the brain just from the brain signals alone. If we can actually now, like we are for generative AI, generate the brain signals versus receiving them, imagine going after Parkinson's, right? And where your quality of life is so poor, right? Could you actually have an intervention where now AI could actually help with the signals in the brain? I totally see that, right? And I think, if people have chronic pain, can you cancel it out? It's just neural. And so the idea is, I think that's where it's a situation where it's severe. I think that would be probably the first area. I think what you read about in science fiction books where you just jack into the universe and just interact, I don't see that happening. Just because the technology advances so soon, you wouldn't want to biologically commit yourself to one particular interface. But if you have an interface that allows you to attack something that dramatically improves your quality of life, people will line up to solve it. That's my personal point of view.
Thank you. Anyone else have any other questions? Oh, somebody in the back? Oh, excuse me.
Yeah.
Sherman?
The results that come out of AI, particularly in healthcare, it's based on input and assumptions that are made. So how do we guard against the probability of incorrect assumptions made by AI, especially in something as important as cancer or NeauxCancer?
Great question. So I guess to iterate the question is like, how do you validate what the AI is producing for you? Before I worked on the healthcare area, I spent a lot of time with NASA, and NASA was like, "There's no way we're going to use AI on those ships, right? I just don't trust this stuff." And it took 26 projects, and when the lander finally lands, AI looks around and goes, "There's a good place to land." They don't trust it. They take the image, they run it through something they've trusted for 30 years, and validate. Okay, now I'll choose that. And what NASA told me, and I just latched onto it a few years ago. He's a CTO of Langley. He said, "I get it now." So what? He goes, "AI is an idiot savant." So you take it at your tumor board, at your sim board, and you sit down and it goes, "I think this is going on. Here's the research." That is just an idea that may have come from anyone else. Now you take that to a doctor and a professional. They look at that like anything else and evaluate it like an idea they just came up with, like in the shower. I think that's where I think that in that way you can reduce the search space for the doctors. And for the very same reason, just like driverless cars, I don't see AI in the very near future being the diagnostician. Now, there are countries like India and Saudi Arabia that are looking at where there's no care for certain populations. And where there's no care, can you restrict it sufficiently? So antibiotic, antidiarrheal, some basic things. If you detect that, could you actually do the diagnostic and ship the medicine directly for someone who has no care at all? And when they do, could you have rooms full of doctors that QA the recommendation by the doctor saying, here's somebody came in, we think they need this. Like, no, they're surfing for drugs. No. You know what I'm talking about, right? So that's kind of where it's headed. But I think your intuition is right. Like, you don't want AI directly to the patient, but you want it as a tool. And if you treat it like NASA, I think it's extremely powerful. Because we're seeing it's now starting to, like we talk about drug discovery, imagine cutting it in half, right? Same thing for diagnostics. Could you cut the diagnostics for a complex case from weeks into minutes, right? But have the doctors make the final call. So that's, and I think also there are tools that try to validate it more, but if you got to really think of these tools as, like, I don't know some of your reasoning when you give an idea, I'll just take it and we evaluate as a team to evaluate it.
Thank you.
Thanks, everybody.
It's